Close your eyes for a moment. Picture yourself standing where you are right now. Your home, your street, your city. Now imagine everything around you buried under ice so thick you could stack 10 buildings on top of each other and still not reach the surface. The ice is everywhere, crushing buildings, covering highways, freezing the air itself. There are no cars, no planes, no sounds except the howling wind that tears across an endless white desert. This isn't some distant planet in a science fiction movie. This is Earth. This is where you're sitting right now, just 20,000 years ago. London was ice, New York was ice, Paris, Tokyo, Mumbai, all of it frozen solid. But here's what most people don't know. That Ice Age, the one with woolly mammoths and saber-toothed tigers, wasn't even the worst one. It wasn't the first, and it definitely won't be the last. Earth has frozen over completely, not once, but multiple times. We're talking about a planet so cold that even the oceans turned into solid ice. A world where the sun rose every morning but couldn't warm anything because everything reflected its light back into space like a giant mirror. Picture a marble spinning through space, white, silent, dead. That was Earth. Now here's the crazy part. We're alive. You, me, every person, every animal, every tiny insect exists today because something, somehow, survived those frozen nightmares. Life was almost erased completely. It hung on by the thinnest possible thread, hiding in the darkest, strangest places you can imagine. How did it survive? Why did the ice finally melt? And most importantly, could it happen again? These aren't just random questions about ancient history. Understanding the ice ages changes everything about how we see our planet today. It explains why certain animals live where they do. It shows us how incredibly fragile and incredibly tough life can be at the same time. And it gives us clues about what's happening to Earth right now, as our climate shifts faster than it has in thousands of years. Before we dive in, I want you to do something. Look around your room. Look at the walls, the floor, the things you own. All of this exists because the ice melted. Human civilization, cities, farms, art, technology, everything only became possible because Earth warmed up after the last ice age. We've only had about 10,000 years of stable, comfortable climate. That's nothing in Earth's history. We're living in a tiny warm gap between ice ages, so let me ask you this: what happens next? Are we heading into another freeze, or are we breaking the pattern completely? The answers might surprise you, and they definitely matter for everyone alive today and everyone who'll come after us. Get ready, we're going back in time to explore Earth's coldest, most dangerous chapters. This is the story of ice, survival, and the planet that just won't quit. Let's go back, way back, further than you've probably ever imagined. We're talking about 2.5 billion years ago. That's not a typo, 2.5 billion years. To put that in perspective, dinosaurs lived only 65 million years ago. Humans. We've only been around for about 300,000 years. Compared to what we're about to explore, humans are brand new. We just got here. At this time, Earth looked nothing like the planet you know. There were no trees, no grass, no flowers, no animals walking around, not even fish swimming in the oceans. The land was completely bare, just rock, dust, and more rock. It was a dead, empty world, at least on the surface. But something was alive down in the oceans. Tiny, microscopic organisms called bacteria and archaea. They were simple, just single cells floating around, doing their thing. They didn't have brains, eyes, or any complex parts. But they were alive, and they were about to change everything. These little microbes had developed a new trick: photosynthesis. They figured out how to use sunlight to make energy, and when they did this, they released something as a waste product. That something was oxygen. Now, here's where it gets interesting. Today, we think of oxygen as essential for life. We breathe it every second. We'd die without it. But back then, oxygen was poison. Seriously. Most of the life that existed at that time couldn't handle oxygen. It killed them. But these photosynthesizing bacteria didn't care. They kept multiplying, kept making oxygen, and slowly but surely, oxygen started building up in the atmosphere. Scientists call this the Great Oxidation Event, and it was one of the most important moments in Earth's history. Here's the problem though. Before all this oxygen showed up, Earth's atmosphere was full of methane. You might know methane as natural gas, the stuff people use for cooking and heating. Back then, methane was everywhere in the air, and it was doing something crucial, keeping Earth warm. The sun at that time was weaker than it is today, maybe about 70 to 80% as bright. If Earth didn't have greenhouse gases like methane trapping heat, the planet would have been frozen solid. Methane was literally Earth's blanket, holding in warmth that would otherwise escape into space. But oxygen and methane don't get along. When oxygen meets methane, they react. They break each other down. As more oxygen filled the air, it destroyed the methane, and as the methane disappeared, Earth lost its blanket. The temperature started dropping. At first, it probably wasn't dramatic. Maybe it got a little cooler at the poles. Snow started falling in winter and not completely melting in summer. Year after year, the snow piled up, compressing into ice. The ice sheets started spreading. And here's where things got really bad. Ice is white. White surfaces reflect sunlight back into space instead of absorbing it. So as more ice formed, less sunlight was absorbed, which made the planet even colder, which created even more ice. This is called the ice albedo feedback loop, and once it started, it was almost impossible to stop. Scientists believe this process might have taken only a few thousand years. In geological terms, that's incredibly fast. Imagine watching time-lapse footage of Earth from space. You'd see white ice spreading from the poles like spilled milk across a table, moving faster and faster, swallowing continents, covering oceans, racing toward the equator. Eventually the ice reached the tropics. The entire planet from the North Pole to the South Pole was covered in ice. This is what scientists call Snowball Earth. Try to picture it. The whole planet, frozen. Not just frozen like Antarctica is frozen today. Antarctica still has exposed rock, liquid ocean nearby, and some areas that occasionally get warm enough for snow to melt. No, this was total ice. A frozen crust covering land and sea, stretching in every direction, unbroken. If you could stand on that ice and look around, you wouldn't see mountains, you wouldn't see the ocean. You wouldn't see any landmarks at all. Just ice, flat, white, endless ice going all the way to the horizon. Above you, the sky would be crystal clear because there was no moisture in the air to form clouds. The sun would look small and dim, struggling to provide any warmth at all. At night, the temperature would plunge even further. Without clouds to trap heat, the cold would become absolute. If you could measure it, the temperature might drop to 50 or 60 degrees below 0 Celsius, maybe even colder in some places. And the silence. My God, the silence. No wind rustling through trees because there were no trees. No birds singing because there were no birds. No waves crashing because the oceans were solid. No rivers flowing because all the water was ice. Nothing moved, nothing made sound. The planet had become a frozen tomb. Now, you might be wondering, how do scientists know all this actually happened? After all, we're talking about events from billions of years ago. We don't have photographs. We don't have written records. How can anyone be sure? The evidence is in the rocks. Geologists have found ancient rock formations called glacial deposits all over the world, including in places that are near the equator today. These rocks show signs of being scraped and moved by glaciers, huge sheets of ice that grind across the land like giant sandpaper. The thing is, glaciers only form in extremely cold conditions. Finding evidence of glaciers at tropical latitudes tells us something extraordinary happened. Scientists have also found something called cap carbonates sitting on top of these glacial deposits. These are layers of limestone that form in warm, shallow oceans. So you've got ice-related rocks on the bottom and warm ocean rocks right on top. That's like finding evidence of a blizzard and a heat wave happening back to back. It suggests the planet went from totally frozen to relatively warm in a geological instant. There's also evidence in the chemical signatures of rocks. When scientists analyze the ratios of different isotopes, different versions of atoms in ancient rocks, they can figure out what the temperature and conditions were like when those rocks formed. The data points to dramatic cooling events multiple times in Earth's early history. Now, there's still debate about exactly how frozen Snowball Earth got. Some scientists think the entire surface was covered in ice several meters thick. Others argue for a slushball Earth scenario, where thin ice near the equator might have allowed a little sunlight to penetrate into the water below. The exact details matter to researchers, but for our purposes, the big picture is clear. Earth experienced freezing so severe that ice reached from pole to pole. It was a planetary disaster. And yet somehow life didn't die. Think about that for a second. Life on Earth was still primitive, just microbes. Nothing fancy, but it survived one of the most hostile environments imaginable. No sunlight reaching the surface, no liquid water accessible anywhere above the ice. Temperatures far below freezing for millions of years. How? Where could anything possibly live? The answer lies beneath the ice, in the oceans below, and in some of the most extreme environments on Earth. But before we explore that, I want you to understand just how close life came to being wiped out completely. If the freeze had been just a little worse, if conditions had been slightly different, life might have ended right there. Earth would have become a dead, frozen ball spinning through space with nothing alive on it. No trees would ever grow, no animals would ever walk, no humans would ever exist. The entire future of life, including you and me, depended on microbes finding a way to survive in the darkness beneath the ice. That's where we're going next. So the planet is frozen, ice covers everything. The surface is a wasteland. Nothing moves, nothing grows. By all logic, life should be over. But it's not. Deep below the ice, in the pitch-black depths of the frozen oceans, life is hanging on, barely, but hanging on. Here's the thing about water that saved everything. Water is weird. Most substances get denser when they freeze. They sink. But water does the opposite. When water freezes into ice, it actually becomes less dense. That's why ice cubes float in your drink. That's why icebergs float in the ocean. And that's why life survived Snowball Earth. When the oceans started freezing during this catastrophic cooling, they froze from the top down, not from the bottom up. The surface ice formed a thick crust, probably several meters thick, maybe even thicker in some places, but underneath that ice, liquid water remained. Think of it like this. The ice sheet became a lid on top of the ocean. It sealed the water below, keeping it separate from the frozen hell above. The weight of the ice pressing down, combined with the residual heat from Earth's interior, kept the deep ocean liquid. And that's where life retreated, but it wasn't easy. The conditions beneath the ice were brutal in their own way. There was no sunlight, so photosynthesis, the process that most life depends on today, was impossible. Any microbes that relied on sunlight were out of luck. They either evolved a new way to survive or they died. The microbes that made it were the extremophiles, organisms that had already adapted to live in the harshest conditions Earth could throw at them. Some of these microbes lived near volcanic vents on the ocean floor, where superheated water rich in chemicals poured out from cracks in Earth's crust. These weren't your average everyday spots. These were the most extreme places on the planet. Imagine being at the bottom of the ocean, in complete darkness, with pressure so intense it could crush most living things. The water coming out of these volcanic vents can be hot enough to melt lead, over 400 degrees Celsius in some cases. On the surface, water boils at 100 degrees Celsius, but deep underwater, the pressure is so high that water stays liquid even at these insane temperatures. For most life, these conditions would be instant death. But for certain microbes, this was paradise. These organisms didn't need sunlight, instead they used a process called chemosynthesis. They fed on chemicals like hydrogen sulfide, methane, and iron that bubbled up from inside the earth. They extracted energy from these chemicals the same way we extract energy from food. It wasn't fast, it wasn't efficient, but it worked. Around these volcanic vents, tiny communities of microbes clustered, forming colonies. They reproduced slowly, probably taking hundreds or even thousands of years for a population to double. Time didn't matter though, there was nowhere to go, nothing to do except survive. And survive they did, for millions of years. Let me repeat that, millions of years. Life survived in these isolated pockets beneath the ice for longer than humans have existed, longer than dinosaurs ruled the earth, longer than you can probably wrap your head around. These microbes sat in the dark, waiting, while the surface remained frozen solid. There may have been other refuges too. Some scientists think that pockets of liquid water might have existed within the ice itself, especially near volcanic areas where heat from below could melt small channels and chambers. Think of it like a frozen lake with cracks and holes where water still flows underneath. Life might have clung to those little niches as well. There's also the possibility that some microbes survived in the tiny spaces between ice crystals. Water doesn't freeze perfectly. It leaves microscopic gaps and channels where liquid water, loaded with salt and other chemicals, remains unfrozen even at extreme cold. These briny pockets might have housed some of the toughest bacteria, waiting out the freeze in spaces smaller than the width of a human hair. What's really remarkable is how life adapted. These weren't complex organisms. They didn't have brains that could think about survival. They didn't plan or strategize, but through random mutations and natural selection, they developed incredible abilities. Some bacteria could shut down their metabolism almost completely, entering a state similar to suspended animation. They could survive without eating, without growing, without doing much of anything for thousands of years. Then, when conditions improved slightly, they'd wake up and start functioning again. Others developed protective proteins that prevented ice crystals from forming inside their cells. Ice crystals can pierce cell membranes and destroy the delicate machinery inside, but these antifreeze proteins kept the microbes safe. Still others learned to live on almost nothing, surviving on the tiniest amounts of energy, scraping by on whatever chemicals they could find. This period of time, with life barely hanging on in the darkness, lasted for somewhere between 10 million and 100 million years. Scientists aren't exactly sure. Dating rocks from that far back is difficult, and there's a lot of uncertainty. But even on the low end, 10 million years is an incomprehensibly long time. To give you perspective, modern humans have been around for maybe 300,000 years. Recorded human history, everything from the pyramids to the moon landing, covers only about 5,000 years. Life survived under Snowball Earth ice for thousands of times longer than human civilization has existed. Think about the odds. If any one of a dozen different factors had been slightly different, life would have gone extinct. If the ice had been just a bit thicker and blocked all volcanic vents. If Earth's interior had cooled just a bit more and stopped producing heat. If the microbes hadn't already evolved to survive extreme conditions. But everything lined up. The microbes made it. And because they made it, everything else became possible. Every plant, every animal, every human being alive today exists because those microbes refused to die. Now, here's the question that must be on your mind. If the planet was frozen solid, if life was trapped beneath miles of ice, how did anything ever change? What broke the freeze? You'd think that once the planet froze over, it would stay frozen forever. After all, ice reflects sunlight, keeping things cold, which makes more ice, which reflects more sunlight. It's a vicious cycle that just feeds itself. So what stopped it? The answer came from below, from the restless, churning interior of the Earth that never stops moving. volcanoes. Even while the surface was frozen, even while the oceans were locked under ice, the inside of the Earth kept right on churning. Magma moved, tectonic plates shifted, and volcanoes erupted. They punched through the ice, sending lava and ash onto the frozen surface. More importantly, they released gases into the atmosphere: carbon dioxide, water vapor, and other greenhouse gases. On a normal Earth, these gases get absorbed quickly. Plants take in carbon dioxide, oceans absorb it, rain washes it out of the air and into the ground. But on Snowball Earth, none of that could happen. There were no plants, the oceans were covered by ice, rain couldn't fall because all the moisture was locked up in ice. So the carbon dioxide just kept building up. Year after year, century after century, millennium after millennium, volcanoes kept pumping CO2 into the atmosphere. And slowly, very slowly, the greenhouse effect kicked in. Carbon dioxide traps heat from the sun, preventing it from escaping back into space. As the concentration increased, the planet started warming up. It took millions of years. But eventually, the temperature rose just enough that ice at the equator, the part of the Earth closest to the sun, started to melt. And once it started melting, everything changed fast. The first cracks appeared at the equator. After millions of years of unbroken white, the ice finally began to give way. It probably started small, tiny patches of dark rock or water appearing here and there. But those small patches made a huge difference. Remember the ice albedo feedback that froze the planet in the first place? Well, now it started working in reverse. Dark surfaces absorb sunlight instead of reflecting it. So when those first patches of ice melted and exposed dark rock or liquid water underneath, they absorbed more heat. That heat melted more ice around them, which exposed more dark surface, which absorbed more heat, which melted even more ice. The feedback loop that froze the planet now became the feedback loop that melted it. Scientists think this thawing might have happened incredibly fast by geological standards, maybe just a few thousand years. That sounds like a long time to us, but remember, the freeze lasted for millions of years. So, in comparison, the thaw was practically instant. Imagine watching a time-lapse of Earth from space. The white ice starts breaking apart near the equator. Dark streaks appear. They spread. The white retreats toward the poles, faster and faster, like someone hit the fast-forward button. The frozen marble starts showing blue again as the oceans opened up. As the ice melted, water vapor got back into the atmosphere. Clouds formed for the first time in millions of years. Rain fell. Rivers started flowing again. The whole water cycle, evaporation, clouds, rain, rivers, oceans, kicked back into gear. And something else happened too. All that carbon dioxide that had built up over millions of years was still in the atmosphere, way more than there should be. Earth went from an icehouse to a greenhouse in geological eye blink. The temperature swung wildly in the other direction. The planet got hot. Really hot. Way hotter than today. This greenhouse period probably lasted for a while, maybe tens of thousands of years, before things eventually balanced out again. But here's what matters: life had a chance again. The microbes that survived beneath the ice suddenly had opportunities. Sunlight reached the oceans, photosynthesis became possible. The microbes that could use sunlight started thriving, multiplying, spreading across the newly melted oceans. This is where the story gets even more interesting. Some scientists believe that these harsh snowball Earth events actually drove evolution forward. Life was forced to adapt or die. The organisms that developed new tricks, new ways to survive, new ways to use energy, were the ones that made it through. After the ice melted, those survivors found themselves in a world with way less competition. A lot of the old microbes that couldn't handle the freeze had died off. The survivors could spread out, diversify, and evolve into new forms. Evidence suggests that complex cells, the kind of cells that eventually led to plants, animals, and humans, appeared not too long after snowball Earth events. that might not be a coincidence. The extreme stress of freezing might have pushed evolution to find new solutions, new levels of complexity. It's a bit like how pressure creates diamonds. The Snowball Earth events were catastrophic, but they may have also created the conditions for more advanced life to develop. But here's the thing, this didn't just happen once. Earth froze over multiple times during this period of its history. Scientists have evidence for at least 2 major Snowball Earth events, possibly more. Each time, the pattern was similar. Something triggered cooling, ice spread across the planet, life retreated to survive, volcanoes eventually warmed things back up, and the ice melted again. Why did it keep happening? Scientists aren't completely sure, but it probably has to do with the fact that Earth's systems were still young and unstable. The balance between greenhouse gases and ice was delicate. It didn't take much to tip things one way or the other. Each freeze-thaw cycle probably lasted between 10 and 100 million years. And each time life survived, it came back a little different, a little more diverse, a little more prepared for whatever came next. Eventually, Earth's climate stabilized somewhat. The atmosphere found a better balance. Oxygen levels steadied. The wild swings between icehouse and greenhouse became less extreme. Life got more complex. Multicellular organisms appeared, then animals, then plants, then everything we see today, but the Snowball Earth events left their mark. Those ancient freeze-thaw cycles changed the chemistry of the oceans. They redistributed nutrients. They created new environments. They tested life in ways nothing else could. And they proved something important. Life is incredibly, stubbornly, impossibly resilient. Think about what we've just covered. Earth went from a living, breathing planet to a frozen, dead-looking ball, and then back again. Not once, but multiple times. And through it all, life hung on. It hid in the darkest, strangest places. It waited, it adapted, and when the ice finally broke, it came roaring back. This is the power of life. This is what makes it so special. It doesn't give up, it finds a way. Even when the entire planet turns against it, even when every condition seems wrong, life persists. But here's something else to think about. Those ancient Snowball Earth events were natural. They were caused by changes in atmospheric chemistry, by shifts in Earth's systems that happened slowly over millions of years. Life had time to adapt. It had places to hide. What we're going to explore next is different. We're going to jump forward in time, past those ancient freezes, to the ice ages that shaped the world we know today. These are the ice ages that created woolly mammoths and saber-toothed cats. The ice ages that early humans had to survive. The ice ages that built the landscape you see outside your window. These ice ages were different from Snowball Earth. They weren't as extreme. The entire planet didn't freeze over, but they were still massive, still powerful, and still shaped life in profound ways. And the really interesting part, these ice ages didn't happen randomly. They came in cycles, regular patterns driven by forces we'll explore in the next chapter. Understanding these cycles helps us understand not just the past, but also what might happen in the future. So let's jump forward about 2 billion years. Let's leave the primitive Earth behind and visit a world that's starting to look more familiar. A world with continents, oceans, animals, and eventually us. Fast forward, we're leaving the ancient primitive Earth behind and jumping to a time that's much more recent, at least in geological terms. We're now in a period that started about 2.6 million years ago and technically continues to this day. Scientists call it the Quaternary period, but most people know it by a simpler name, the Ice Age. Now, here's something that confuses a lot of people. When we say Ice Age, we usually picture woolly mammoths, cave people, and glaciers everywhere, and that's accurate. But technically, we're still in an Ice Age right now. Yeah, you read that right, we're living in an Ice Age. How can that be when it's warm outside and there aren't glaciers covering your city? The answer is simple. An Ice Age doesn't mean the whole planet is frozen all the time. An ice age is any period when Earth has permanent ice at the poles. Right now, we have ice in Antarctica and Greenland. That ice doesn't melt completely, even in summer. That counts. We're in an ice age, just in a warm phase of it. Within ice ages, the climate swings back and forth between colder periods, called glacials, when ice sheets expand, and warmer periods, called interglacials, when ice sheets shrink. Right now, we're in an interglacial, a warm break between the cold spells. The last major glacial period, the one with mammoths and all that, ended only about 12,000 years ago. That's incredibly recent if you compressed Earth's entire 4.5 billion year history into a single 24-hour day. The time since the last ice age ended would be less than a quarter of a second. We're talking about yesterday, basically. So why does the ice come and go in these cycles? What makes Earth freeze up, then warm up, then freeze again, over and over? For a long time, nobody knew. It was one of science's biggest mysteries. Then, in the early 1900s, a Serbian scientist named Milankovitch figured it out. Milankovitch realized that Earth's relationship with the Sun isn't constant. It changes in very specific, predictable ways. Earth's orbit around the Sun isn't a perfect circle. It's slightly elliptical, kind of egg-shaped, and that shape changes over time. Sometimes the orbit is more circular, sometimes more stretched out. This cycle takes about 100,000 years. Earth also wobbles as it spins. You know how a spinning top wobbles as it slows down? Earth does the same thing, except it takes about 26,000 years to complete one wobble. This wobble changes which parts of Earth point toward the Sun during different seasons. And there's one more factor, the tilt of Earth's axis. Right now, Earth is tilted at about 23.5 degrees. But that tilt changes over time, swinging between about 22 degrees and 24.5 degrees. This cycle takes about 41,000 years. Each of these changes affects how much sunlight different parts of Earth receive at different times of year. Individually, the changes are small. But when they line up in certain ways, they can trigger big shifts in climate. Here's the key insight. Ice ages don't start because Earth gets cold everywhere all at once. They start when summers in the northern hemisphere get just cool enough that winter snow doesn't completely melt. Year after year the snow piles up. It compresses into ice. Glaciers start forming and spreading. Once glaciers start growing, that ice albedo feedback kicks in again, just like we saw with Snowball Earth, but less extreme. The ice reflects sunlight, keeping things cooler, which allows more ice to form. The glaciers keep expanding until they cover huge areas of North America, Europe, and Asia. At the peak of the last glacial period, about 20,000 years ago, ice sheets were unbelievably massive. In North America, the ice stretched from the Arctic down to where New York City is today. In some places, the ice was more than 2 miles thick. 2 miles. That's taller than any building humans have ever constructed, and it covered entire regions. Imagine standing in Chicago 20,000 years ago. You'd be under a mile of ice. The weight of that ice pressed down on the land so hard that it actually deformed Earth's crust, pushing it deeper into the mantle. Even today, thousands of years after the ice melted, the land in places like Scandinavia and Canada is still slowly bouncing back up, rising a few millimeters per year. The ice locked up so much water that sea levels dropped by about 120 meters. That's almost 400 feet. Coastlines were completely different. You could have walked from England to France because the English Channel was dry land. Indonesia and mainland Asia were connected. Alaska and Russia were connected by a land bridge called Beringia. The whole map of the world looked different, but then, when Earth's orbital cycles shifted into the right configuration, summers got warmer again. The ice started melting, glaciers retreated. Sea levels rose, and the world transformed once more. This pattern freeze, thaw, has repeated over and over for the past 2.6 million years. Scientists have identified at least 50 different glacial, interglacial cycles during this time. Each cycle takes about 100,000 years on average, roughly 90,000 years of cold, with ice sheets expanding, followed by about 10,000 years of warmth, like what we're experiencing now. Think about that ratio. We spend most of the time in the cold phase. The warm, comfortable climate we enjoy today is actually the unusual part. It's the brief pause between ice ages. Now, you might be wondering, if these cycles are driven by Earth's orbit and those orbital changes are predictable, can we predict when the next ice age will come? The answer is yes, sort of. Based on orbital mechanics, scientists expected that we should be gradually cooling toward another glacial period over the next few thousand years. But here's where things get complicated. Humans have changed the equation. By burning fossil fuels and releasing huge amounts of carbon dioxide into the atmosphere, we've added so much greenhouse gas that we've basically overridden the natural cooling cycle. Instead of slowly sliding into the next ice age, we're warming up fast. Some scientists think we might have delayed the next ice age by tens of thousands of years, maybe even cancelled it entirely. That might sound like good news. Who wants another ice age, right? But it's actually more complicated than that. Our climate system evolved during these ice age cycles. Life adapted to them. And changing the pattern so dramatically could have consequences we don't fully understand yet. But we're getting ahead of ourselves. Before we dive into modern climate change, we need to explore what happened during those glacial periods. Because while the ice was spreading, something incredible was happening. Life was adapting in the most remarkable ways. The world during the last glacial maximum wasn't just a frozen wasteland. It was alive, strange, magnificent creatures roamed landscapes that no longer exist. And somewhere in the middle of all that ice and cold, early humans were trying to survive, learning to hunt, make fire, and tell stories that would eventually become the foundation of civilization. The giants were walking, and we need to meet them. But before we do, I want you to understand something important. Those Ice Age animals weren't just bigger versions of animals we have today. They were specifically adapted to cold, harsh environments. Their bodies, their behaviors, their entire existence was shaped by ice. And when the ice melted, when the climate warmed up about 12,000 years ago, most of them went extinct. The world changed too fast. They couldn't adapt quickly enough. Within just a few thousand years, a blink of an eye in evolutionary time, the giants disappeared. Why did that happen? Were humans responsible? Was it climate change? Was it a combination of both? These questions matter because we're living through something similar right now. Our climate is changing faster than it has in thousands of years, and species are going extinct at rates we haven't seen since the dinosaurs disappeared. Understanding what happened to the Ice Age megafauna, the giant animals, might help us understand what we're facing today. So let's go back to that frozen world. Let's walk across ice sheets and frozen grasslands. Let's watch mammoths grazing, saber-toothed cats hunting, and giant ground sloths lumbering across landscapes that don't exist anymore. Let's meet the giants. Picture this: you're standing on a vast grassland. But this isn't like any grassland you've seen today. There's no Amazon rainforest here, no Sahara Desert, no prairies like we have in North America now. This is something different. This is the Mammoth steppe, the largest ecosystem that has ever existed on Earth. During the last ice age, this grassland stretched from Spain all the way across Europe, through Asia, over the Bering Land Bridge, and into North America. One continuous frozen grassland covering millions of square miles. It was cold, dry, and windy, but it wasn't empty. Far from it. This was the land of giants. The most famous resident, of course, was the woolly mammoth. You've probably seen pictures: massive elephants covered in thick, shaggy hair with enormous curved tusks. They looked like something out of a fantasy novel, but they were real, and they were everywhere. Woolly mammoths weren't just big, they were perfectly designed for the Ice Age. Their thick coat had two layers, long outer hairs that could be 3 feet long, and a dense undercoat that trapped heat like a blanket. They had a layer of fat beneath their skin, sometimes 4 inches thick, that insulated them from the cold. Their ears were small, much smaller than modern elephants, to reduce heat loss. They even had a flap of skin that could cover their anus to protect it from the cold. Evolution thought of everything. Their tusks could grow up to 15 feet long and weighed over 100 pounds. Males used them to fight each other for mates, to dig through snow to reach grass underneath, and to strip bark off trees. Fossils of mammoth tusks sometimes show wear patterns that tell us how they used them, like reading the biography of an individual animal that lived thousands of years ago. Mammoths were social, just like modern elephants. They lived in herds led by older females. They communicated with rumbles and trumpets. They probably mourned their dead. We've found evidence of mammoths standing around the bodies of deceased herd members, refusing to leave, but they weren't alone out there on the frozen steppe. Woolly rhinoceroses roamed the same landscapes. These weren't like the rhinos in Africa today. These were stocky, muscular animals covered in thick hair, with 2 horns on their snouts, one long, one short. The front horn could grow over 3 feet long. Fossils show they used it to sweep snow away from vegetation like a shovel. Giant ground sloths, not the little slow-moving animals we see in trees today, but massive creatures the size of elephants, lived in the Americas. Some species could stand on their hind legs and reach heights of 20 feet. They had enormous claws, over a foot long, that they used to strip leaves from trees. Despite their size, they were herbivores, gentle giants that probably moved slowly and spent most of their time eating. Cave bears lived throughout Europe, hibernating in caves during the worst winters. They were enormous, bigger than modern grizzly bears, with massive skulls and powerful jaws. Despite their fearsome appearance, evidence suggests they were mostly vegetarian. Irish elk roamed across Europe and Asia. Elk is actually a misleading name. They were more closely related to deer. But what made them special were their antlers, the largest of any deer species that ever lived. The antlers could span 12 feet from tip to tip and weigh up to 90 pounds. Every year, males shed these massive antlers and grew them back. The amount of calcium and energy required to do that must have been staggering. And then there were the predators. Saber-toothed cats, multiple species of them, hunted across the Americas. The most famous Smilodon had canine teeth up to 7 inches long. Those teeth weren't for biting and tearing like modern big cats. They were precision instruments for killing. Smilodon would use its powerful neck muscles to drive those teeth deep into the throat of prey, severing major blood vessels. It was quick and efficient. Cave lions prowled Europe and Asia, bigger than modern lions, with no manes, perfectly adapted for cold climates. They hunted mammoths, bison, and horses. Dire wolves hunted in packs across North America. They were heavier and more robust than modern grey wolves, with stronger jaws designed to crush bones. Short-faced bears in North America were possibly the largest predators to ever walk on land. Standing on their hind legs, they could reach 12 feet tall. They had long legs, longer in proportion to their body than any other bear, which meant they could run fast. Some scientists think they might have been scavengers, using their size to scare other predators away from kills, but others argue they were active hunters. This world was alive with megafauna, animals weighing over 100 pounds. And not just a few species, dozens of them. North America alone had over 40 species of megafauna. Eurasia had even more. It was a crowded, competitive, dangerous, and absolutely magnificent world. The question is, how did all these giant animals survive in such a cold environment? Size helped. Larger animals have a lower surface area to volume ratio, which means they lose heat more slowly than small animals. A mouse loses heat quickly because it has a lot of surface area compared to its body size. An elephant stays warm because it has relatively little surface area compared to its massive body. This is called Bergmann's rule, and it's why animals in cold climates tend to be bigger than their relatives in warm climates. But size alone wasn't enough. These animals had other adaptations too. Many had thick fur or fat layers for insulation. Some, like mammoths, had specialized blood vessels in their ears and trunks that could restrict blood flow to reduce heat loss. Others, like woolly rhinos, had compact body shapes with short legs and tails to minimize exposure. And crucially, they had food. The mammoth steppe was cold, but it was productive. The dry, cold climate created grasslands that were surprisingly rich. Grasses, sedges and flowering plants covered the landscape. There was enough vegetation to support enormous populations of herbivores. We know this because we found fossil evidence of massive herds. At some sites, scientists have uncovered thousands of mammoth bones in a single location, suggesting they lived in huge numbers. The biomass, the total weight of all living things on the mammoth steppe, might have been higher than in any modern ecosystem. This abundance of herbivores supported a healthy population of predators. The whole ecosystem was in balance, more or less. Animals died, predators ate them or scavengers did. Nutrients returned to the soil, plants grew, herbivores ate the plants, and the cycle continued. It had worked this way for hundreds of thousands of years, through multiple glacial cycles. Species came and went, evolved and adapted, but the basic pattern remained stable, until it didn't. About 50,000 years ago, something new entered this picture, something that would change everything. Humans. Not modern humans, living in cities with technology. These were our ancestors, Homo sapiens, who had evolved in Africa and were now spreading across the world. They were hunter-gatherers, living in small groups, making stone tools, using fire. They were smart, really smart, smarter than any other animal on Earth, and they were about to meet the giants. Let's be clear about something. Early humans were not at the top of the food chain when they first arrived in Ice Age landscapes, not even close. They were fairly small, average height around 5'5" or so. They didn't have claws, sharp teeth, thick fur, or natural armor. They couldn't outrun most predators. They couldn't fight a cave lion or a short-faced bear and win. In a one-on-one physical confrontation with most Ice Age megafauna, humans would lose, badly. But humans had something else. Something that made them more dangerous than any predator: intelligence, cooperation, and the ability to use tools. Early humans entering Ice Age Europe and Asia weren't walking into paradise. They were walking into one of the harshest environments on Earth. Winters were brutal. Temperatures could drop to 40 or 50 degrees below zero. Food was scarce during winter months. Water froze solid. The wind cut through anything that wasn't properly protected, and yet humans survived. Not just survived, they thrived. How? First, fire. Control of fire was probably the single most important technology early humans had. Fire provided warmth, obviously, but it did so much more. It allowed humans to cook food, which made nutrients easier to digest and killed parasites. It provided light, extending the day and allowing activities after sunset. It scared away predators. No animal wants to mess with fire. And it created a social center where people could gather, talk, tell stories, and strengthen bonds. Archaeological evidence shows humans were using fire extensively by at least 400,000 years ago, probably earlier. By the time they entered Ice Age Europe, around 45,000 years ago, they were experts. They knew how to start fires, maintain them, transport burning embers from place to place, and use them strategically. Second, clothing. Humans are tropical animals originally from Africa. We don't have thick fur. In Ice Age climates, we'd freeze to death without protection. So humans learned to make clothing from animal skins. They used stone tools to scrape hides clean, then sewed them together using bone needles and animal sinew as thread. We found bone needles dating back at least 40,000 years. These weren't crude instruments. They were carefully crafted, with eyes for thread, precisely shaped. The clothing they made was sophisticated, layered garments fitted to the body, designed to trap heat while allowing moisture to escape. Some cultures made waterproof outer layers from intestines or bladders. Others created insulated boots and gloves. Clothing was probably decorated too. We've found shells, beads, and pigments at archaeological sites, suggesting people adorned their clothing. This wasn't just practical, it was cultural, aesthetic, human. Third, shelter. Humans couldn't just hide in caves all winter. Although they did use caves when available, they needed portable shelter that could move with them as they followed game animals. In treeless areas of the Mammoth steppe, where wood was scarce, humans got creative. They built structures from mammoth bones and tusks. These weren't small huts. Some of these bone structures used hundreds of bones from dozens of mammoths. Heavy skulls formed the foundation. Long limb bones and tusks were propped up as supports. Hides were stretched over the framework and weighted down with more bones. One archaeological site in Ukraine contains a dwelling made from nearly 400 mammoth bones. Building it must have taken weeks, maybe months. It wasn't temporary, this was a long-term home. Inside these shelters, humans created surprisingly comfortable spaces. They dug the floor down slightly for insulation. They built hearths for fire in the center. With smoke holes above, they created sleeping platforms raised off the cold ground. They stored food, tools, and other supplies. These weren't primitive savages barely scraping by. These were people with sophisticated technology, complex social organization, and the ability to plan for the future. Fourth, and perhaps most importantly, cooperation and communication. Humans hunted in groups, using strategy and coordination. They developed specialized tools for different tasks: spear points for hunting, scrapers for processing hides, needles for sewing, blades for cutting. They created art, lots of it. Cave paintings, carved figurines, decorated tools. The oldest known cave paintings date back at least 40,000 years. People painted animals on cave walls: mammoths, horses, bison, lions, with stunning realism and detail. Some paintings show hunting scenes, others might have had spiritual or ritual significance. This art tells us something crucial. These people had language, abstract thinking, culture. They passed down knowledge from generation to generation. They told stories. They had beliefs, rituals, identities, and they were incredibly successful hunters. This is where the story gets complicated and controversial. Starting around 50,000 years ago, as humans spread across the world, megafauna started going extinct. The timing is suspicious. Woolly mammoths disappeared from mainland Europe around 14,000 years ago. Giant ground sloths in the Americas went extinct about 11,000 years ago. Mammoths survived on isolated islands until about 4,000 years ago, but only in places humans didn't reach. Was this a coincidence? Or did humans hunt these animals to extinction? Scientists have been arguing about this for decades. It's called the overkill hypothesis, and here's the case for it. Humans were skilled hunters. We found kill sites with multiple mammoth carcasses, showing humans could take down these giants. Spear points embedded in bones prove humans hunted mammoths, bison, horses, and other megafauna. When humans arrived in new territories, Australia, the Americas, isolated islands, mass extinctions followed within a few thousand years. The correlation is hard to ignore. Large animals reproduce slowly. Mammoths had long pregnancies and raised one calf at a time. If humans killed even a small percentage of adults each year, the population couldn't replace itself. It would spiral toward extinction. But there's another side to this debate. Climate change happened at the same time. The ice was melting. The mammoth steppe was transforming into forests and tundra. The ecosystem that had supported megafauna for hundreds of thousands of years was disappearing. Maybe the extinctions were caused by habitat loss, not hunting. Or maybe it was both, climate change weakened populations, and human hunting pushed them over the edge. The truth is, we don't know for certain. It was probably a combination of factors that varied from species to species and place to place. What we do know is this: by about 10,000 years ago, most of the Ice Age megafauna were gone. The mammoths, the giant sloths, the saber-toothed cats, the short-faced bears, extinct. The woolly rhinos, the cave lions, the dire wolves, extinct. The world that had existed for hundreds of thousands of years vanished in less than 10,000 years, and humans were left standing in a world that suddenly felt very empty. But humans adapted. We always adapt. As the ice melted and forests replaced grasslands, humans shifted from hunting megafauna to hunting smaller game, deer, rabbits, birds. They gathered more plants, nuts, and berries. They fished, and eventually, about 10,000 years ago, humans made another enormous leap: agriculture. They stopped following animals and started planting crops. They domesticated animals: sheep, goats, cattle, pigs. They built permanent settlements. They developed pottery, metallurgy, writing. Civilization began. All of this was possible because the climate had stabilized. The Ice Age was over, the glaciers had retreated, temperatures warmed up and stayed relatively stable. The last 10,000 years, called the Holocene, have been extraordinarily stable by Earth's standards. Temperatures haven't swung wildly. Sea levels have been consistent. This stability allowed humans to develop agriculture and build civilizations. Everything you see around you, cities, technology, art, science, everything exists because the climate has been stable for 10,000 years. But here's the uncomfortable truth, that stability might be ending. The Ice Ages teach us that Earth's climate can change dramatically. We've seen how ice can advance and retreat, how ecosystems can transform, how species can go extinct when conditions shift too quickly. And right now, we're changing the climate faster than it's changed in thousands of years. We're conducting an experiment with our planet, and we don't fully know how it will end. The Ice Ages aren't just ancient history. They're a warning. They show us what's possible. They show us how quickly things can change. And they show us that even species that seem invincible, like woolly mammoths that survived for hundreds of thousands of years, can disappear when the world changes too fast. So let's talk about that. Let's talk about what happened when the ice finally melted. Let's talk about what scientists learn from studying ancient ice. And let's talk about what the frozen ages teach us about the world we're creating today, because the story isn't over. In many ways, it's just beginning. About 20,000 years ago, Earth reached its coldest point in the most recent glacial cycle. Ice sheets covered massive portions of the northern hemisphere. Sea levels were 400 feet lower than today. The world looked completely different, and then, slowly, at first, everything started to change. The ice began to melt. This wasn't a sudden event. No one woke up one morning to find the glaciers gone. It took thousands of years, but by the standards of geological time, it happened incredibly fast. Within about 8,000 years, the enormous ice sheets that covered North America and Europe had mostly disappeared. Sea levels rose by those 400 feet, entire landscapes transformed. This period is called deglaciation, and it's one of the most dramatic transformations in Earth's recent history. So what triggered it? Why did the ice start melting? Remember those orbital cycles we talked about, the Milankovitch cycles? Around 20,000 years ago, Earth's orbit and tilt shifted into a configuration that allowed more summer sunlight to hit the northern hemisphere. Summers got warmer. Not dramatically warmer, just enough that winter snow started melting more each year instead of piling up. At first, the changes were subtle. The edges of ice sheets began retreating. Small lakes formed on the surface of glaciers, but once the melting started, feedback loops kicked in. As ice melted, it exposed dark ground underneath. That dark ground absorbed more sunlight instead of reflecting it, which caused more warming, which melted more ice. The same feedback that helped freeze the planet now worked in reverse. And there was another factor, carbon dioxide. During glacial periods, CO2 levels in the atmosphere drop. Scientists aren't entirely sure why. It probably has to do with changes in ocean circulation and the carbon cycle, but ice core data clearly shows that CO2 levels during glacial maximums are much lower. Then during warm periods, as the ice started melting, CO2 began rising. Warmer oceans released dissolved CO2. Changes in ocean circulation brought deep water to the surface, releasing more CO2. Thawing permafrost released carbon that had been locked in frozen soil. Plants grew back on newly exposed land, but not fast enough to absorb all the CO2 being released. More CO2 meant more greenhouse warming, which accelerated the melting. The ice sheets didn't just slowly melt and trickle away. Sometimes they collapsed catastrophically. Imagine a wall of ice, 2 miles thick, as it melts. Water pools on top of it, drilling down through cracks and weakening the structure. Eventually, huge sections break off and collapse. Lakes trapped behind ice dams suddenly burst through, releasing floods of biblical proportions. One of these events, called the Missoula floods, happened in North America around 15,000 years ago. A massive lake trapped behind an ice dam in what's now Montana suddenly burst through. The amount of water released was equivalent to all the rivers in the world combined, flowing for several weeks. The flood carved enormous channels through Washington state, moving boulders the size of houses and reshaping the entire landscape. Geologists can still see the scars today. Similar floods happened all over the world as ice dams failed and glacial lakes drained. These weren't gentle, gradual changes. They were violent, catastrophic events that happened within days or weeks. The melting ice had another major effect. It flooded the oceans with massive amounts of fresh water. Normally, ocean water has a specific salinity. It's salty because of dissolved minerals, but when glaciers melt, they release fresh water. Suddenly dumping enormous amounts of fresh water into the ocean can disrupt ocean currents. And that's exactly what happened multiple times during deglaciation. Ocean currents are like a global conveyor belt, moving heat from the equator toward the poles. Warm water flows north on the surface, cools down, becomes denser, sinks, and flows back south at depth. This circulation is crucial for regulating climate, but when you dump fresh water into the North Atlantic, it dilutes the salty water and prevents it from sinking. The conveyor belt slows down or even stops, and when that happens, the climate goes haywire. Around 12,800 years ago, something called the Younger Dryas began. Just as the world was warming up, temperatures suddenly plunged again. Not as cold as the full glacial period, but cold enough to halt the warming and even cause some glaciers to advance again. This cold snap lasted about 1,200 years. Then, just as suddenly as it started, it ended. Temperatures shot back up. The warming resumed. Scientists think the Younger Dryas was triggered by a massive influx of fresh water into the North Atlantic, possibly from a glacial lake in North America that suddenly drained. This fresh water disrupted ocean circulation, causing regional cooling. When the circulation restarted, warming resumed. The point is, climate doesn't change smoothly. It can have sudden jumps, reversals, unexpected shifts. The system is complex, with many moving parts, and sometimes those parts interact in surprising ways. As the ice melted and the climate warmed, life responded. Plants that had survived in small refuges during the Ice Age began spreading. Trees that had been confined to southern regions moved north, following the retreating ice. Within a few thousand years, vast forests covered areas that had been glacial wastelands. Animals followed the plants. Some species adapted to the new conditions, others didn't. This is when most of the Ice Age megafauna went extinct. We talked about this in the last chapter, the woolly mammoths, the saber-toothed cats, the giant sloths. Between about 15,000 and 10,000 years ago, they disappeared. Some scientists argue climate change was the main driver. The mammoth steppe ecosystem was collapsing. As the climate warmed and became wetter, grasslands turned into forests and bogs. Animals adapted to cold, dry grasslands couldn't survive in these new environments. Others point to human hunting as the primary cause. Humans were spreading across the globe, and extinctions followed their arrival with suspicious timing. The truth is probably a combination. Climate change stressed populations by destroying habitats and food sources. Human hunting pushed already weakened populations over the edge. The megafauna were caught between two threats, and most couldn't survive both, but life is resilient. New species evolved or migrated into the newly available habitats. The world that emerged from the Ice Age was different from before, but it was rich with life, and humans were thriving. As the climate stabilized around 10,000 years ago, humans made one of the most important transitions in our history. We developed agriculture. In multiple places around the world, independently, humans figured out they could plant seeds, grow crops, and harvest food on purpose, instead of searching for wild plants. They domesticated animals, turning wild wolves into dogs, wild cattle into cows, wild sheep into livestock. Why did agriculture develop when it did? The timing isn't a coincidence. During the Ice Age, with unpredictable climate and harsh conditions, agriculture wouldn't have worked. You can't plant crops if winters are brutal and summers are short. You can't maintain herds if grasslands keep shifting. But when the climate stabilized in the Holocene, the warm period we're still in, agriculture became possible. People could predict seasons. They could plan ahead. They could invest time and energy into planting crops. Knowing those crops would grow, agriculture changed everything. It allowed humans to produce more food, which supported larger populations. People settled down in permanent villages instead of moving constantly. They had time to develop new technologies, pottery, metallurgy, weaving. They created complex social structures, specialization of labor, trade networks. Civilization began. All the ancient civilizations you've heard of, ancient Egypt, Mesopotamia, the Indus Valley, ancient China, emerged during this stable Holocene climate. The pyramids, the Great Wall, the invention of writing, mathematics, philosophy, art, all of it happened because the climate was stable enough to allow it. This is crucial to understand. Human civilization exists because we've had 10,000 years of unusual climate stability. Before the Holocene, the climate was too unstable. During the Ice Age, temperatures swung wildly. Droughts could last for centuries. Cold snaps could return suddenly. It was impossible to plan long-term because you never knew what next year would bring. But for the past 10,000 years, temperatures have stayed within a relatively narrow range. There have been variations, some periods warmer, some cooler, but nothing like the wild swings of the Ice Age. That stability is ending. Right now, we're in the early stages of the fastest climate change Earth has experienced in thousands of years. And this time, it's not caused by orbital cycles, or volcanic eruptions, or natural processes. It's caused by us. Humans have released so much carbon dioxide into the atmosphere by burning fossil fuels that we've fundamentally altered the planet's energy balance. We're adding greenhouse gases faster than at any time in the ice core record, faster than during the deglaciation that ended the last ice age. And we're seeing the effects. Glaciers are melting. Ice sheets in Greenland and Antarctica are losing mass. Sea levels are rising. Weather patterns are shifting. Ecosystems are struggling to adapt. The ice ages teach us that Earth's climate can change dramatically. They show us what's possible when the planet warms or cools. They give us a window into how life responds to those changes. And they provide us with tools, actual physical tools, to understand what's happening today. Those tools are buried deep in the ice itself, waiting to tell their story. If you want to understand Earth's climate history, you need to go to the ice, not just any ice. You need ancient ice, ice that formed thousands or even hundreds of thousands of years ago and has stayed frozen ever since. Ice that has preserved, layer by layer, a record of what Earth's atmosphere was like when that ice formed. The best place to find this ice is Antarctica and Greenland, where ice sheets thousands of meters thick have been building up for hundreds of thousands of years. Scientists drill down into these ice sheets, extracting long cylinders of ice called ice cores. These cores are like time machines. Each layer represents a year, sometimes even a single season. By analyzing the ice, scientists can read Earth's climate history going back almost 1 million years. How does it work? When snow falls, it traps tiny bubbles of air. As more snow piles on top, the older snow gets compressed into ice, but those air bubbles remain sealed inside. Those bubbles contain samples of Earth's ancient atmosphere, the actual air from thousands of years ago. Scientists can extract those air bubbles and measure their composition. They can see exactly how much carbon dioxide, methane, and other gases were in the atmosphere at different times in history. The ice itself also contains clues. Water molecules come in different isotopes, slightly different versions of the same molecule. The ratio of these isotopes changes depending on temperature. By measuring isotope ratios in the ice, scientists can calculate what the temperature was when that snow fell. There are other indicators too. Dust trapped in the ice shows how windy it was, which tells us about atmospheric circulation patterns. Volcanic ash layers mark major eruptions. Chemical traces show ocean productivity. Pollen grains reveal what plants were growing nearby. All of this information is preserved layer by layer in the ice. The longest ice core ever drilled comes from a site in Antarctica called Dome C. Scientists drilled down 3,190 meters, almost 2 miles, and extracted ice that's 800,000 years old. That's 800,000 years of continuous climate data, year by year. What does this data tell us? First, the ice ages really did come in cycles. The ice core shows clear patterns of warm and cold periods, matching what Milankovitch predicted. Every 100,000 years or so, there's a glacial maximum followed by rapid warming. The pattern repeats over and over. Second, carbon dioxide and temperature are tightly linked. When CO2 levels are high, temperatures are warm. When CO2 levels are low, temperatures are cold. This isn't surprising. We know CO2 is a greenhouse gas, but seeing it so clearly in 800,000 years of data is powerful evidence. During glacial periods, CO2 levels drop to about 180 parts per million, ppm. During warm interglacials, they rose to about 280 ppm. This cycle repeated consistently over hundreds of thousands of years. Here's what makes today so alarming. Current CO2 levels are over 420 ppm. That's higher than at any point in the ice core record. Higher than at any point in the last 800,000 years. Probably higher than any time in the last several million years. We've pushed CO2 levels far outside the natural range that existed during the ice ages. We're in completely uncharted territory. Third, climate change can happen fast, really fast. The ice cores show that at the end of the Younger Dryas, that sudden cold snap we talked about, temperatures in Greenland rose by about 10 degrees Celsius, 18 degrees Fahrenheit in just a few decades. That's an enormous change in an incredibly short time. This tells us the climate system can have sudden shifts, tipping points where it jumps from one state to another rapidly. It's not always a slow, gradual process. Fourth, small changes can have big effects. The orbital variations that trigger ice ages are tiny, changes in sunlight of just a few %. But those small changes get amplified by feedback loops until the whole planet transforms. This is relevant today because we're making much bigger changes to the climate system than those small orbital variations. If small natural changes can trigger ice ages, what will our large, rapid changes trigger? Ice cores aren't the only tool scientists use. There are many others. Ocean sediment cores contain fossils of tiny marine organisms. The chemistry of their shells tells us about past ocean temperatures and chemistry. Some sediment cores go back millions of years. Lake sediments preserve pollen, which shows what plants were growing in the area. Changes in pollen types indicate changes in climate. Tree rings record annual growth. Wide rings mean good growing conditions. Narrow rings mean stress from drought or cold. Some trees live thousands of years, providing long climate records. Coral reefs grow in layers, like tree rings. Their chemistry records ocean temperature and salinity. Stalagmites in caves grow slowly over thousands of years, recording changes in rainfall and temperature in their layers. All these different sources agree with each other. They all tell the same basic story. Earth's climate has changed dramatically over time. Those changes follow predictable patterns driven by natural processes, and life has always responded to those changes by adapting, migrating, or going extinct. But there's something else these records tell us, something that should make us pay attention. Climate can change faster than species can adapt. We see this in the fossil record. During rapid climate changes, extinction rates spike. Species that were common disappear. New species emerge or migrate in from elsewhere. Ecosystems reorganize themselves, often into configurations that have never existed before. The Ice Age megafauna extinctions are a perfect example. When conditions changed too quickly, whether from climate, human hunting, or both, most of them couldn't adapt fast enough. They went extinct. Today, we're creating conditions that are changing even faster than during the end of the Ice Age. And we're doing it at a time when species are already stressed by habitat loss, pollution, invasive species, and other human impacts. Scientists estimate that species are going extinct at rates 100 to 1,000 times higher than the natural background rate. Some call this the sixth mass extinction, comparing it to the event that killed the dinosaurs. The ice cores show us that what we're doing is unprecedented. For 800,000 years, CO2 never rose above 280 ppm. In just the last 150 years, since the Industrial Revolution, we've pushed it to 420 ppm. That's a 50% increase in the blink of an eye. And it's still rising, faster now than ever before. The ice has one more lesson to teach us, perhaps the most important one. Ice itself matters. The Greenland and Antarctic ice sheets aren't just frozen water sitting there doing nothing. They're active parts of the climate system. They reflect sunlight, cooling the planet. They influence ocean currents. And they contain enough frozen water to raise sea levels by about 70 meters if they melted completely. Let me repeat that, 70 meters, that's about 230 feet. Every coastal city in the world would be underwater. New York, London, Tokyo, Mumbai, Shanghai, Miami gone. Billions of people would have to relocate. Now, scientists don't think the ice sheets will melt completely anytime soon, but they are melting. Greenland is losing about 280 billion tons of ice per year. Antarctica is losing about 150 billion tons per year. These numbers are accelerating. The ice cores show that in the past, when climate warmed, ice sheets responded by melting. Sea levels rose. Coastlines moved. The process took thousands of years, but it happened. Today, we're warming the planet faster than during past natural changes. The ice sheets will respond. We're already seeing it happen. The question isn't if it's how fast and how much. This brings us to the final part of our story. What do all these lessons from the ice ages mean for us today? What should we do with this knowledge? Because knowledge without action is just trivia. The ice ages aren't just fascinating history. They're a warning. They're a guide. They're showing us what happens when climate changes, and they're asking us, what are you going to do about it? Let's be very clear about something. The ice ages are not ancient, irrelevant history. They're a preview, a guidebook, a warning label on the package of our planet. Everything we've explored, the freezing, the thawing, the extinctions, the climate cycles matters right now, today, because we're actively changing the same systems that controlled those past changes. Here's what the Ice Ages teach us. Lesson 1. Small changes can have massive consequences. The orbital variations that trigger ice ages are tiny. We're talking about changes in sunlight reaching Earth of just a few percent. But those small changes get amplified through feedback loops until the entire planet transforms. Ice reflects sunlight, making things cooler, which creates more ice. Warming melts ice, exposing dark ground, which absorbs more sunlight, which causes more warming. These feedback loops can amplify small initial changes into enormous effects. Today, we're not making small changes. We're making huge changes, releasing carbon that took millions of years to accumulate in just a couple of centuries. If small natural changes can flip the planet between ice ages and warm periods, what will our large, rapid changes do? We're about to find out. Lesson 2. Life adapts, but not infinitely and not instantly. Life survived Snowball Earth. Life survived the Ice Age cycles. Life is incredibly resilient and creative in finding ways to persist. But, and this is crucial, many individual species don't make it. Extinction is real, it happens, and it happens most often when conditions change too quickly. The Ice Age megafauna survived hundreds of thousands of years of climate variability. They made it through multiple glacial cycles. But when the climate changed rapidly at the end of the last Ice Age, combined with human hunting pressure, most went extinct in just a few thousand years. Today, we're changing the climate even faster than that, and species are already stressed by habitat loss, pollution, and other human activities. They're trying to adapt, trying to migrate, trying to survive. But many won't make it. We're already seeing it: coral reefs bleaching and dying, Arctic animals losing their ice habitat, species shifting their ranges toward the poles or to higher elevations, trying to follow the climate. They're adapted too. The ice ages show us that when climate changes too fast, extinction follows. Lesson 3. Ice sheets matter. A lot. During ice ages, ice sheets grew and locked up water, dropping sea levels by 400 feet. When the ice melted, sea levels rose by that same amount, flooding coastlines and forcing human populations to migrate. Today, we still have massive ice sheets in Greenland and Antarctica. They're melting. Not quickly by human standards, we're talking millimeters per year, but they're melting and the rate is accelerating. The ice cores show that ice sheets have melted before during warm periods. They also show that once melting starts, it can accelerate through feedback loops. Meltwater on the surface creates pools that absorb more sunlight, melting more ice. Ice shelves that hold back glaciers can collapse, allowing land ice to flow faster into the ocean. If we push warming far enough, we could trigger irreversible melting of one or both ice sheets. That wouldn't happen overnight. It would take centuries or millennia, but once started, it might be impossible to stop, and the consequences would be catastrophic. A meter of sea level rise displaces hundreds of millions of people. Several meters displaces over 1 billion. 70 meters, the total if all ice melted, would reshape civilization entirely. We're not there yet, but we're heading in that direction, and the ice ages show us it's possible. Lesson 4. Tipping points are real. The ice core record shows sudden climate changes, periods where temperature jumped dramatically in just a few decades. The Younger Dryas is one example, a sudden cold snap triggered by changes in ocean circulation lasting over 1,000 years, then ending almost as abruptly as it began. These sudden changes show that climate doesn't always move smoothly. There are tipping points, thresholds where the system flips from one state to another rapidly. Scientists worry we might be approaching tipping points today. Things like collapse of major ice sheets, shutdown of ocean circulation patterns like the Gulf Stream thawing of permafrost, releasing huge amounts of methane and CO2. Amazon rainforest dieback, turning a carbon sink into a carbon source. Collapse of ocean ecosystems like coral reefs. The scary thing about tipping points is that you often don't know you've crossed one until it's too late. Once the system tips, it might be impossible to reverse. The ice ages warn us these tipping points exist. Climate can change suddenly. We should not assume change will be slow and manageable. Lesson 5. Humans are adaptable, but civilization needs stability. Our ancestors survived the Ice Age. They adapted to harsh conditions, developed new technologies, and thrived. Humans are incredibly adaptable, but, and this is important, they survived in small groups, moving as needed without permanent infrastructure or complex supply chains. They could pack up and migrate when conditions changed. Modern civilization is different. We have cities with millions of people. We have infrastructure, roads, buildings, power grids that can't easily move. We have agriculture that depends on predictable seasons and rainfall. We have supply chains that connect the whole world. All of this exists because the Holocene has been stable. We built our entire civilization during this unusually stable warm period. When climate becomes unstable, when droughts last years instead of months, when sea levels rise and flood cities, when heat waves make regions uninhabitable, when rainfall patterns shift and disrupt agriculture, civilization struggles. We saw this on small scales in history. The collapse of the Mayan civilization was partly caused by droughts. The fall of the Akkadian Empire in Mesopotamia followed a massive drought. These were regional climate shifts affecting pre-industrial societies. Today, we're creating global climate change affecting an interconnected, industrialized world of 8 billion people. The risks are much larger. Lesson 6. We have unprecedented power and responsibility. Here's something the Ice Ages couldn't teach our ancestors. Humans can actually influence global climate. For most of history, climate was something that happened to humans. We had to adapt or move or suffer. We had no control. But starting with the Industrial Revolution, that changed. By burning fossil fuels, we began adding CO2 to the atmosphere. At first, the effect was tiny, but it accumulated, year after year, decade after decade, century after century. Now, we've changed atmospheric CO2 by 50%. We've warmed the planet by over 1 degree Celsius. We're melting ice sheets, we're shifting weather patterns, we're changing the chemistry of the oceans. We have become a force of nature. Our actions affect the entire planet. This gives us power, but also responsibility. We can't claim ignorance. We know what CO2 does. We know what happened during past climate changes. We have the science, the data, the understanding. The ice cores are right there, telling us exactly what happened when CO2 changed in the past. And they're telling us that what we're doing now is unprecedented in at least 800,000 years. So what do we do? The Ice Ages provide context, but they don't give us easy answers. They show us what's at stake, how the system works, what's possible, but deciding what to do is up to us. Some facts are clear. CO2 levels are higher than they've been in hundreds of thousands of years. Temperatures are rising faster than during natural past changes. Ice sheets are melting and sea levels are rising. Weather patterns are shifting. Species are struggling to adapt. If we continue on our current path, impacts will get much worse. We have options. We can reduce emissions by switching from fossil fuels to renewable energy, solar, wind, nuclear, and other clean sources. We can increase efficiency, using energy more wisely. We can protect and restore ecosystems that absorb carbon, forests, wetlands, grasslands. We can develop technologies to remove CO2 from the atmosphere. None of these solutions are easy. They require investment, coordination, political will, and changes to how we live. But they're possible. We have the technology, we have the knowledge. What we need is the collective decision to act, to prioritize long-term sustainability over short-term convenience, to recognize that we're part of nature rather than separate from it, to accept responsibility for the planet we're shaping. The Ice Ages teach us humility. Earth is old. It has transformed many times. It has survived catastrophes that would seem unimaginable to us. But those transformations took millions of years and caused massive extinctions. We are newcomers to this story. Our entire species has existed for only a few 100,000 years. Our civilizations are only 10,000 years old. We're incredibly young, incredibly fragile, incredibly dependent on stable climate. The ice will come again someday. The glaciers will advance. The cycle will continue. But for now, in this brief warm interval, we have a choice. We can learn from the past, we can act in the present, we can shape the future. The frozen ages have taught us everything we need to know. The ice cores have given us clear warnings. The extinctions have shown us what happens when change comes too fast. Now it's up to us to apply those lessons. The ice is melting, the future is unwritten. And the story continues. So here we are, at the end of this journey through Earth's frozen past. We started 2.5 billion years ago, watching the planet freeze into a snowball, life retreating to the dark depths of the ocean, barely hanging on. We saw how volcanoes eventually broke the freeze, how life came roaring back, how these extreme events might have even pushed evolution forward. We jumped forward to the ice ages most people know about, the cycles that created woolly mammoths, saber-toothed cats, and frozen grasslands stretching across continents. We walked with giants and watched early humans learn to survive in one of Earth's harshest environments. And we arrived at today, looking at melting ice sheets, reading ancient ice cores, and confronting the reality that we're changing our planet faster than it's changed in thousands of years. The story is extraordinary. But more than that, it's relevant, it's urgent, it matters right now. Because understanding the ice ages isn't just about knowing cool facts about the past. It's about understanding the planet we live on. It's about recognizing that climate isn't static. It changes, sometimes dramatically, sometimes quickly. It's about seeing that life is both incredibly resilient and incredibly vulnerable. The Ice Ages show us that Earth is capable of transformations we can barely imagine. From frozen wastelands to lush ecosystems and back again, each transformation took time, but they happened, they were real, and they're not over. Right now, we're living in a warm pause between Ice Ages. If natural cycles continued, we'd eventually slide into another glacial period over the next few thousand years. But we've altered those natural cycles. We've pumped so much CO2 into the atmosphere that we've essentially delayed or cancelled the next ice age. That might sound like good news. Who wants glaciers covering Chicago again? But it's not that simple. We haven't just stopped the ice age cycle. We've pushed temperatures higher and faster than the system is designed to handle. The organisms alive today, including us, evolved during ice age cycles. We're adapted to a world where temperatures swing between certain ranges. We depend on ecosystems that developed during those cycles. We built civilizations during an unusually stable warm period. When we push climate outside those ranges, when we change things faster than natural past changes, we're entering unknown territory. We're running an experiment, and we're all part of it. The Ice Ages offer us a mirror. They show us what happens when climate changes. They demonstrate that feedbacks can amplify small changes into huge ones. They prove that tipping points are real. They remind us that extinction follows rapid change, but they also show us that life endures, that adaptation is possible, that even in the darkest, coldest moments, the spark of existence persists. We're not helpless. We're not passive victims of climate. We have knowledge, technology, and choice. The same intelligence that figured out how to read ice cores, that decoded Earth's climate history, that put humans on the moon, that intelligence can solve this problem. We can develop clean energy. We can protect ecosystems, we can adapt our societies to changing conditions, but we have to choose to do it. We have to decide that the future matters as much as the present. We have to recognize that we're shaping the world not just for ourselves, but for hundreds of generations to come. The Ice Ages teach us to think in deep time, to consider thousands and millions of years, not just quarterly profits or election cycles, to understand that our actions today will echo through time long after we're gone. So here's what I want you to take away from this. First, be amazed. The story of Earth's climate is genuinely incredible. Ice covering the entire planet, mammoths wandering frozen grasslands, humans surviving against impossible odds. It's all real, and it's all part of your heritage. Second, be humble. We're newcomers to this planet. We've been here for a geological instant. Earth has endured catastrophes that would wipe us out completely. We're not the masters of nature, we're its inhabitants. Third, be informed. The science is clear. The evidence is overwhelming. We know what's happening and why. Ignore the noise, ignore the denial, and pay attention to what the ice cores, the fossils, and the data are telling us. Fourth, be active. You don't have to be a climate scientist to make a difference. Support clean energy. Vote for leaders who take climate seriously. Reduce your own carbon footprint where you can. Talk to others about what you've learned. Small actions add up. And finally, be hopeful. Yes, the challenges are enormous. Yes, we've already caused damage that will take centuries to undo. But the story isn't over. We still have time to change course. We still have agency. We still have hope. The frozen ages are ending. The mammoths are gone. The ice has retreated, but life continues. Adapting, evolving, persisting. We're part of that story now. We're writing the next chapter. What do we want it to say? That we saw the warnings and ignored them. That we had the knowledge but lacked the will. That we chose short-term comfort over long-term survival. Or that we learned from the past. That we acted when it mattered. That we became the first species capable not just of understanding our impact, but of taking responsibility for it. The Ice Ages have given us the blueprint. The lessons are clear. The evidence is overwhelming. The choice is ours. Thank you for taking this journey through Earth's frozen past. I hope it's changed how you see ice, how you understand time, and how you think about our planet's future. The story continues, and you're part of it. What happens next is up to all of us.